Alright, so we're going to come up with the next equation for kinematics with a constant acceleration. I'm going to use that equation. The v final is equal to v initial plus at. My final velocity is equal to my initial velocity plus the acceleration times time. The rate in which or the change in my velocity, if you want. You can think of this as simply how much my velocity changes by. And instead of talking about velocities, I want to talk about position or displacement. Okay? Well, we know one thing. We know something about velocity. I've got it written right up here. Velocity is displacement over time, or the change in position over time. I'm going to go with the second definition on this, so I'm going to say, aha, this velocity is nothing more than the change in position over time. Once again, I'm talking about calculus. I'm doing the abbreviation for change. Well, it's not really abbreviation. It's a better definition for change. It's the instantaneous change. So dx dt. Wait a minute. dx dt. Why not dy dt or dz dt? Or even, for that case, dr dt. Here's the cool thing. If I'm talking about velocity, I'm talking about change in displacement over time. I'm talking about position in time. I'm talking about a direction. So every time I come up with this equation, with whether I'm talking about velocities, whether I'm talking about accelerations, whether I'm talking about positions, I'm talking about vectors. So I got to keep track of direction. So I'm coming up with an equation here for the x direction. So if this velocity is the change in the x direction with respect to time, then this acceleration has to be the acceleration in the x direction. This velocity has to be the velocity in the x direction. This position has to be the position in the x direction. So we're doing it for the x direction, but it turns out that all of those equations are going to look identical to each other. But they're independent. They're orthogonal. Y direction, x direction. They're independent of each other. They don't interact. So when I come up with an equation for the x direction, it may look identical to that of the y direction, but they're not the same equation. They're not the same terms. They're not the same variables. One set of variables is only going to work for the x direction. Another set of variables is only going to work for the y direction. So we got to make sure that you keep those separate. So anyway, dx dt, well, is equal to v initial. Now, here's the thing that throws a lot of people off. Everybody really quickly wants to put dx dt there. It's not. It's initial velocity. When I did this equation, and you can go back and check, this vi, this initial velocity, is a constant. It doesn't change with respect to time. How fast I'm moving originally doesn't change with time. It's how fast I moved originally. So it's nothing more than a constant. So that's just going to be vi plus, okay, how about the acceleration? It's constant. It doesn't change with respect to time. Hence, kinematics with a constant acceleration. Cool? Now, to talk about position, I'm going to do the exact same thing I did with velocity. I'm going to say, well, I want to take an integration with respect to this. Well, to do it to one side, I have to do it to the other. So I have the integration with respect of vi dt plus the integration of a t dt. Cool? Oh, there's a dt in here. Okay, it's going to go away real quick. So there's a dt. So really quick, that's going to go away and that's going to go away, and I'm left with the integration of dx is equal to vi is a constant. I can bring it out front. Acceleration is a constant. I can bring it out front. But does time change with respect to time? Yes. Time keeps on increasing. So a integration of t dt. Okay? If I do the calculus on that, I'm going to get x final is equal to vi t, because here's my t right there. When I take the integration of dt, I get t, plus, now I'm taking the integration of t with respect to t. That means this number goes up, its exponential goes, as exponent goes up to 2, and then that comes out front. Okay? So that ends up giving me a 1/2 a t squared plus a constant. Okay? So that means x final is equal to the initial velocity times time plus 1/2 the acceleration times time squared plus a constant. Using the same logic we did with velocity, I know that that constant is going to be initial position. Okay? So that turns out to be x final is equal to x initial plus v initial t plus 1/2 a t squared. Cool? That's the answer. That's our third equation. That means that the final position depends on a lot of things. The final position of an object depends on where it started, the initial position, how fast was it moving at that given time, and then the rate of change of that velocity and then some. Okay? So we have this rate of change of velocity, and then we have then some, this time. So if you look at this equation really quickly, over long periods of time, this term, this acceleration term, is going to play some major importance with its displacement. That's why NASA is currently trying to build solar cell technology using magnetic fields to absorb solar radiation. Has tremendously small acceleration values. It's not like you're strapping yourself into a rocket and sending yourself into orbit, but it experiences those accelerations for incredibly long periods of time, getting you up to some very, very high speeds. Okay? So, over long periods of time, this is going to have some serious ramifications. Over very short periods of time, these two terms are going to have more implications, they're going to weigh more on your final position than this, not unless that acceleration is massive. Okay, so my third equation. Whoa! Just about fell over there. Okay, there's my third equation. Cool. I'm going to erase this real quick. Oh. And that's it. I'll give you one more equation.